Yeah, that's the reason. So we can have time, you all can have time to learn, you can do time to do some exam prep. Right? Let us look at page 150. Okay? So we are looking at Hooke's law and Young's modulus. So background in this, elasticity of a property. Oh man. Elasticity is the property of a material to return to its original form when force causing the strain is removed. Right? So remember when you compress something, right? You're basically squashing it. Elasticity is the property that makes the material return back when that force is removed. Okay? This only happens if the elastic limit is not exceeded. If the elastic limit is exceeded, permanent deformation occurs. So you know sometimes you have like what must be an example? Say like a spongy material or a metal or even even metal, right? If you have like a block of flimsy metal and if you press it, right, it will eventually return back to its shape, right? Because it's flimsy. Okay, say rubber, right? Rubber. If you press it, it will return back, right? If you pull it, it will return back to its shape. But at a certain point, if you pull it too much, you're gonna see that it doesn't return; it stays that length. Now, what that basically means, it passed the point of its elasticity limit. It's only elastic for a certain point. After it can't return back to its shape. That's what they refer to. So, the elastic limit is the maximum stress for which complete recovery from the strain can still take place. Okay, so elastic limit is when you apply a maximum stress or maximum force on the material and it still returns back to the shape. Hooke's law. So Hooke's law states that for an elastic object, the strain is directly proportional to the stress caused it. So if you increase the stress, if you increase the force, your strain is also going to increase. Okay, that's what they mean by directly proportional. The point at which the strain is no longer proportional to the stress is called your limit of proportionality. So your limit of proportionality is the point at which your strain is no longer proportional to your stress. Okay, Young's elastic modulus. So the ratio of stress divided by strain will be constant for a specific material within the limit of proportionality and is known as Young's modulus for tensile and compressive stresses. It is denoted by the symbol E. So Young's modulus is equal to stress over strain. Right? This is
I thought strain was
Yeah,
what? That's right. This is not shear stress or shear strain. The shear strain. Hey, no, this thing. Tongue twisters, right? So, Young's modulus is equal to stress over strain. Okay? Then you get something on the next page, which is called, it's for shear, right? You get something called the modulus of rigidity. So that will be capital letter G is equal to shear stress over shear strain. Okay? So this is? Okay? So you can see the difference with symbols. Same formulas, it's just different symbols. Right? So Young's modulus, stress over strain, modulus of rigidity, shear stress over shear strain. Good? Good? Then let's say will also be aspects. Okay, is everybody still with me?
yes.
Okay? So far the 6 formulas I taught you, right? Stress is equal to force over area. Strain is equal to your change in length over original length. Shear stress is also equal to force over area. Right? Just symbols are different. is also equal to your change in length over the original length. Just a different symbol, shear strain. Right? Young's modulus, stress over strain. Modulus of rigidity, shear stress over shear strain. That's the 6 formulas you need to know for this. And then obviously you need to know like area of different shapes. Okay? For stress, which type of area we look at?
Cross-sectional.
Cross-sectional area. Everybody understands? Good. Right? I'm on page 151. So, stress and strain graphs. So, when the load on a metal rod of known diameter is gradually increased, the loads and the extensions are recorded. The corresponding stress and strain values may be calculated. So, they basically applied a force onto a metal rod and they kept on applying the force. Okay? So, the stress and strain values for a metal rod, example, the stress and strain value for a metal rod of 2 meter length is as follows. So, the cross-sectional area is equal to 8 times 10 to the 5. Right? In the table, I'm looking at the table. Right? So, the cross-sectional area is equal to that. So, they started off with a load of 20 kilonewtons. And they found that the extension was 0.05. Okay? So, your delta x is 0.05. Stress, how you would have worked it out, you would have taken that force over area. So, you would have taken 20 over 8 times 10 to the minus 5. You would have got 250. Understand? And the strain, you would have taken 0.05 over 2 meters. The change in length over the original length. So what they did, you're all with me, right?
Yeah.
Okay. So what they did was, they kept on increasing the load. So they went from 20 to 40 to 60 to 80, 100, eventually to 200. What can you tell me about the extension when they increased the load?
It's increased by 0.05.
Or, okay, it increased. It increased, right? Your extension increased as your force increased. Stress, what happened to your stress as your force increased or the load increased?
It increases as well.
It also increased. And your strain also increases.
Everything increases.
Everything increased.
So, to a point where it start increasing more.
Yeah. Okay. So the graph that they end up drawing is based on the values that they obtain. So that graph they have, your y-axis is stress, your x-axis is strain. So based on all those values that they worked out, they plotted points, they drew lines connecting the points. Okay? The first part of the graph will be a straight line. The slope of the straight line is the constant of proportionality and is known as the modulus of elasticity. This is the portion of Hooke, or this is a portion over which Hooke's law is obeyed. What is Hooke's law? No.
State that for the elastic objects, the strain is directly proportional to the stress causing it.
Okay? Your strain is directly proportional to the stress causing it. So as your stress increases, your strain also increases. But it increases to the proportionality limit or the elasticity limit. Okay? That's where you start to see that bump in it. Because at that certain point, it's not returning back. That after you reach that certain stress, the shape is not going to go back to its old shape. Okay. In tensile testing, I'm on the top of page 152. In tensile testing, a tensile specimen is used or sample. Right? The shoulders of the specimen are large so that it can be gripped properly, and in between there is a gauge section or of a smaller cross section, and the failure of deformation will take place in the section. Don't worry about that. Right? A typical stress and strain graph. So, that typical stress and strain graph, the stress and strain diagram differs in form for different materials, obviously, right? So, from O to P, that is known as your elastic region. Okay? They tell you over there from O to P, the the proportional limit, the stress and strain graph is a straight line. If the load is removed, there will be no permanent deformation. We explained that. Why? Because of Hooke's law. Okay? It will return back to its shape. The material will return to its original position. Your elastic limit is the point beyond which the material will not go back to its original shape when the load is removed. So where at point E, anything past point E, it will not return back to its original shape. Yield point is the point at which the material will have an appreciable elongation or yielding without an increase in the load. So where the material will get longer even when you increase the load or without increasing the load. Okay? The syllabus only prescribes the stress and strain graph, but the proportional limit and yield point can also be seen on a load extension graph as shown in the figure below. So for the syllabus, you only need to concern yourself with your proportionality limit, where point P is, and your elastic limit. You don't have to worry about that point further where they have U, the ultimate strength, and R and other stuff. Right? That will come in N5 physics. Okay? Right. So you understand the graph there? Yes? You just need to go through it. It's nothing bad. I hardly saw it being tested. What they do test you on is, okay, I'll show you later, right? Okay, so let's do an example, right? So, example 6.10. Example 6.10 tells you that a tensile force of 30 kilonewtons is applied to a rectangular bar. So you have a bar. Right? Tensile force is a pulling force. So the force that's pulling it is equal to 30 kilonewtons. Is applied to a rectangular bar 25 millimeters by 18. So let's say this is 25 millimeters, and from there to there is 18 millimeters, right? The length of the bar is 2 meters, and Young's modulus for the steel is 200 GPa. So Young's modulus is equal to 200 GPa, right? So to convert that into pascals, it's times 10 to the power 9. Okay? So this here in pascals will be equal to 200 times 10 to the power 9. How can I like 200 0, 0, 0, 0, 0, right? Because it will go pascals to kilopascals to megapascals to, I think it's gigapascals, right? And each time you multiply by 10 to the 3. 10 to the 3. 10 to the 3. Right? Okay? So if you want to go from there to there, you multiply by times 10 to the 3 times 10 to the 3 times 10 to the 3, which is times 10 to the 9. Okay? And if you want to go back, you just divide by that. Right? Everybody understands? Okay, so this here is equal to 30,000 newtons. This is equal to 0.018 meters at 0.025 meters. That's also in meters, right? Got everything in our units, yes? Yes. Question asks you to calculate the stress, right? Stress is equal to force over area. We know the force, we know the area, right? We can work out the area, it's just going to be that times that. So this would be 30,000 divided by 0.02 times 0.018, which is
You got anything?
Eight and a lot of threes.
7 trees.
25. Oh, that's why. But 0.02.
sorry.
6 is 8 6.
No, it's not the right answer.
Oh, I can't be the one mistaking it such a
No, because we are putting 0.02. We never put
0.025,
0.025. That's
right?
6.
6. How many sixes?
1, 2, 3, 4, 5, 6.
8.
0.67.
Pascal, which is 66.667 megapascals, right? That's your stress, right? Then they want to know what is the final length due to the tensile force, right? Remember, when this force acts on this object, it's a pulling force. It's going to cause this object to go longer. So its length is going to increase by agree?
What's that? 200.
Delta x.
Oh.
Right. It's going to increase by delta x. Yes?
Yeah.
Right. Its final length would be delta x plus 2.
Yeah.
So we need to get delta x to be able to work that out based on the information we have. Right? Delta x is used in what? Strain. Right? Do we know the strain?
No, but we can calculate.
We can calculate the strain. How can we calculate the strain? We'll use Young's modulus. Right? Young's modulus is equal to stress over strain. Right? So strain would be equal to stress over Young's modulus. We just worked out stress. So that would be equal to that 66.67 all over 200 times 10 to the 9. Okay, in future start giving me like in exponential on 10. Because it'll be so long to write each number. So this one would have been 6,67 times 10 to the 7.
Three recurring. 3.3 recurring times 10 to minus 10.
Minus 10. Minus 3. Minus 3.
Oh, sorry, 4.
Minus 4. So that's 0.000333. And then there's no units for strain. Right? Now that we know strain is equal to your change in length all over your original length. Right? So your change in length will be equal to strain times your original length, which will be equal to 0.000333 times 2, which is meters, right? So its new length or its final length will be equal to 2 plus 0.000666, which is fine. Is that fine?
Oh yeah.
That seems so challenging. That's really
All these,
so badly.
All these formulas go, they won't be included, eh?
No.
No, I don't think those one. They give us nothing. Okay, but you understand the calculation. It's difficult. No, everything is given to us, right?
As long as you already calculated the formula to use.
Yeah.
Yeah. But this one is not so bad because there's not much formulas. And if they're asking you for stress is this. Then you just work it out, right?
But can you take a picture and you can post it?
No, this is science, but so it's not math. I want to. Shame, you look so sad, man. Your math's so bad.
No, after lunch.
Yeah.
See, and you say no, I have maths after that. They will give us science and then you'll suffer with the maths after that. After lunch or whatever, eat or whatever.
No, we'll be jumping off the walls.
Okay. You check out the side, right?
You take both sides. Both sides.
Check it.
How
Guys, so
You know, if they really wanted us to pass this thing, they should give us those.
That makes sense.
Yeah, yeah. They should give us the
Just
formula.
give us the formulas and tell us how to use it, eh?
Yeah, and the answers too.
Nah. But if they give us the formulas, it's fine. Because now you have to like scratch your head. Now, which one do I use here? Aye. There's too many to remember.
And the thing is, they're all very similar.
So it's easy to confuse it. What?
You may explain.
how? I never say anything. I'm keeping quiet today. I never say anything.
Sounds of used to it.
The look
Sounds of used
says it all.
I chocolate, it's expired.
You know why? Because used to keep it.
It's human, that's right.
Then they give the old stuff that they got in the drawers,
Then you-
and they put new ones in the drawers.
I know.
Tell you what's famous for that. The thing is, one from our side, yo, I don't think you all know him, but he passed away. They opened his locker. He had like more than one locker, you know, PPA locker, change room locker. And it was packed with cokes and chocolates. Some of the cokes were actually busted in. Yeah, that's how they used to be. Fact. They started giving those.
Yeah, that's great. Some people don't use their grain metal because you keep the damn thing, it's gonna expire because you can't have it all.
You have to throw it away.
Yeah, eventually it's going. If you try to have a lot of it, you're gonna get sick.
Yeah. So for that time period, that wasn't here. So it was this.
You know, almost every week I saw them cook chocolates for Central Zone. I had to give it to this house to know that give all moments.
You look at us.
Never gave you away.
No,
What did you do?
I mean, every Southern, a lot of stuff.
I gave some of the South Zones.
Southern
I gave Segi, I gave Warren, I gave Ants. Ants was crap.
You used to get the stuff.
We used to eat all the expired stuff every Go in your ship.
I used to give Ants and Stephen Paul. Not Stephen, Mike Paul. Yeah. And because they always take them coming back, bending. I used to give them. I gave Vicky one.
Okay. Can I take out this one?
I'm gonna take you
I have a cold on. Did I?
Right. This is a story. They got this right. Yeah. Example 6.11. A round bar with a diameter of 50 millimeters and a length of 900 millimeters. Right. So initially it was a round bar of 50 with a diameter of 50 and the length was 900. Right. Then they machined the bar to have a square area of 20 millimeter sides for a length of 0.5 meters. So that round bar you had, you put it in the machine, it basically made it into the top part of it into a square bar. So I have my round bar here. Initially this whole portion was a round bar. Right? They put it in the machine for 0.5 meters. Remember the full length would have been 0.9 meters. Right? The 0.5 meters was machined into a square bar. So can you see it now? Okay. Right. Then the stress in the square section due to tensile force is not to exceed 400 MPa. Right? So the stress, that's it, would be 400 MPa, the maximum we can go to. Tensile force is a pulling force. Okay? calculate the stress in the round part. Now, how would you calculate the stress in the round part? Stress is equal to what?
Yeah, so you calculate the stress, so you calculate the force, and then the force applied on the square part will be the same as the
Okay.
force applied on the round.
So, stress is equal to force over area. Right? Remember, the force that's being applied to the round is also being applied to the square. Right? That whole piece of metal or bar or whatever is going to have the same force pulling it. Right? So, the same force that's pulling the round bar will also pull the square bar. Now, stress is equal to force over area. We can work out the area of the square bar. Fine, pi d squared over 4. Of the round bar, pi d squared over 4. We were giving the stress for the square bar. We can work out the area of the square bar. So we can solve for the force. Okay? So, let's see square. Where are square?
UA.
Always on video bad things. For the square bar, stress is equal to force over area.
What should
So-
have drawn the square?
Your force is equal to stress times area. So this should be 400 times 10 to the 6 multiplied by 0.002 squared. Because remember the area of a square is side squared. Right? So even if you say side times side, it's still the same thing as side squared. Right? And then I converted this to 10.6 because I'm getting pascals. Everybody's with me?
Yeah.
Okay? So this is it.
Wow. Oh, interesting. $1,600 newtons.
It's equal to?
1,600.
About
1,600.
600.
Yeah.
Yeah.
You're right, oh. Hey, y'all don't even help me with conversions, y'all, huh? 0.02.
Oh.
Okay.
You're not paying attention, that's it. I'm gonna do a whole wrong section with you. And then check it in. Whatever you give me after that. What is that? 160,000
Yeah, 160
newtons. So that's the
kilonewtons.
force, the tensile force that's pulling this bar, right? So for the, what do you call it, round bar?
Yeah, round bar.
So for the round bar, the stress would be equal to force over area. The force would be 160,000 over pi times 0.05 squared all over 4, which is
First one, 4, 8, 7, 3,
Yo.
0,
81, 48.
48,
8,
7330. 186.
Pascals, right? 1, 2, 3, 4, 5, 6. 81.487. Okay? So that was the stress that was experienced on the square bar. And the stress that was experienced on the, no, that was the stress experienced on the round bar. And your stress that was experienced on the square bar was 400 AP. Okay? And understand what I did? Anybody confused about what I did?
Why is it 400 AP? 81.
No,
The square bar is one.
the square bar is 400 MPa.
Okay.
And this bar here would be
81.
81.
So
Square
there's more.
bar. Right? B. Now they want to know the total extension of the bar if Young's modulus of elasticity is 100 GP. So Young's modulus is equal to 100 times 10 to the 9 pascals. Now they want to know the total extension. So when it pulled, how much did it extend here? And how much did it extend? Okay, something like that. How much did it extend?
Either side.
On either side. Right? So the total extension will be this change in x1 plus the change in x2. Okay? Because remember there will be a different strain applied for it because your stress is different on both sides. Okay? Right. So now we need to work out the strain on each side and then solve for change in x. Okay? Young's modulus should be a constant throughout the whole beam. Okay? So, let's say for the round bar. For round bar, right? We want to work out the strain. Young's modulus is equal to stress over strain. So your strain will be equal to stress over Young's modulus. Your stress in the round bar is this value. Right? It's 81.487 times 10 to the 6 all over 100 times 10 to the 9, which is
4, yeah.
right?
Yeah.
Right. That's the strain. So strain is equal to your change in length over your original length. Right? I'm going to call this change in length 1 because I've got it labeled that. Right? So it's going to be 8.1487 times 10 to the minus 4 times the change in length over the original length, which would have been 0.4 meters. So your change in length at the round bar would be equal to
3.259.
3.25948. That's all.
448. 3.25948.
Yeah, no, not times 10.
But times 10 exponent minus 4.
Times 10 to the minus 4 meters. Right? So that's how much it extended on the round bar. You're all with me?
Yeah.
Sure. Yes, you're okay.
Yeah, we got
Something happened when I go here. All just you fell to sleep or something. Okay.
It's that time of the day.
Right? So now for the square bar. Same story like how we did that one. Its strain would be equal to its stress over Young's modulus, right? Which would be equal to 400 times 10 to the 6 divided by 100 times 10 to the 9, which is 0.4 times 10 to the minus 4. No, 4 times 10 to the minus 4. 4 times 10 to the minus 4. Be 0.4 times 10 to the minus 3.
4, it's 4 times 10 exponent 3 minus 3.
4
times 10 exponent minus 3.
eh? strain. Okay, using a strain will be equal to a change in x2 all over the original length, right? So therefore your change in x2 is equal to your strain multiplied by your original length, which is 4 times 10 to the minus 3. Its original length was 0.5. So x2 is
2 exponent minus 3.
2 times the exponent minus 3 meters, right? So your total extension is equal to x1 plus x2, right? Which would be 3.259 times 10 to the minus 4 plus 2 times 10 to the minus 3, which is
2.3
326 times 10 to the
minus 3
meters, which is approximately 2,326 millimeters. That's how much the beam or the bar extended by. Does everybody understand what I did here? Huh? Yeah, it's a. I feel like it's the hardest thing they could ask you. But on a 900 millimeter bar. I don't think. Right?
But it's logical, right?
Yeah.
It's logical.
Most of the science is there. Does everybody understand what I did? Is anybody confused completely about what I did? I never introduced any new formulas. I'm using the same formulas I used throughout, right? I worked out every other way they could possibly ask you how to do it, right? So you have that all. To be honest, I feel like this is the hardest thing they can ask you. Right? Okay. So, yeah. Let's look at example 6.12. Now example 6, I'm not going to draw the whole graph and stuff on the board, right? You can just go through it. But y'all can redo it when you go home, right? It's similar to how they got that other value. So what they tell you is, the following readings were obtained during a tensile test on a mild steel bar. So when the load was 0, the extension was 0. When they did a load of 30, they got extension. They did a load of 26, they got the value 39 and 60, right? The original diameter of the gauge length section is 26 millimeters. So it's a round bar. It's a round bar that has a diameter of 26 millimeters. The length or the original length is 62 millimeters. Okay. Draw the stress and strain graph. So if you turn over, right? You have your load and your extension that was given to us. Am I right? Okay. We know the diameter of this bar is 26 millimeters, right? And we know the length of the bar is 62 millimeters. So how do you work out stress? Force over area. So you're going to have to take the force of 0 over the area, 13 over the area, 26 over the area, 39 over the area, 60 over the area. So you'll see just above the graph, they worked out the area of the graph. Right? They got a value of 5,31 times 10 to the minus 4 meters squared. Right? Are you seeing it?
Yeah.
Okay? So the area will be constant throughout for this bar because that's the cross-sectional area. All you'll do, you'll take 13 over 5,31 times 10 to the minus 4. You'll get that value of 24,482. Understand? So how they did stress at 13, they got the value there. Can you see that? Where they got stress is equal to force over area. Then they calculated stress at 13, stress at 26, stress at 39, stress at 60. So you can see how they got the values for stress, right?
Yeah.
Not difficult. Understand?
Yes.
That would be right?
Yeah.
Okay. Strain is the change in length over the original length. So all those extensions 0.0121 divided by 0.062, because if you convert the length to meters, it will be what? 0.062. Guys, the length of the bar is how long? 62 millimeters.
Yeah.
If you convert it to meters,
Okay, yeah.
Okay.
0.062.
Right.
So if you take the extension, that's 0.
Oh, yeah.
Well, actually, you don't have to, because it's given to you in millimeters. You just take it as 0.0121 divided by 62. You'll get that ratio, that value, which is your strain. Understand?
Okay.
Okay, so you'll do that 5 times for all those values. And then you plot a graph of stress versus strain. Stress is on your
Y-axis.
y-axis, strain is on your x-axis. Fine?
Now, how do I know which should be on the y-axis, which should be on the x-axis?
When they tell you a graph of something versus something, the first something is always your y-axis, the second something is your x-axis.
Okay.
Say like if I tell you plot the graph of volume versus time, which will be your y-axis, which will be your x-axis? Time, right? Always, that's how you write down when you're drawing a graph. Or normally, sometimes they put it as graph of independent variable versus dependent variable.
The independent is y.
Yeah, no, sorry. Graph of dependent variable versus independent. Because remember, time is the independent value, we controlling that value. The volume is dependent on how much time you would use. In this instance here, your stress or your strain, but because they're directly proportional in this instance, it won't apply. But whatever writing they give you first, draw the graph of stress versus strain. Stress will be your y-axis, x-axis will be strain. Right? Do you understand what I'm saying? Yeah?
Sure.
Right. They got the graph, they plotted their points, they drew a straight line through the points. Okay? Then, so that was that. Then they ask you to determine Young's modulus of elasticity with the aid of the graph. Now remember, from the theory we said before, Young's modulus will be the gradient of the graph. Right? Remember, towards the bottom region where your elasticity appears. So, how I told you to work a gradient in maths, y2 minus y1 over x2 minus x1. So what they did was they took it at a point A. Right? So, they took it at point A. Their one coordinate was 4 times 10 to the minus 4. Okay, so also the graph that they drew on the y-axis, the 0 is supposed to start where the bottom 0 is. You get what I'm saying?
Yeah.
Okay, so when you're counting the numbers, count it like that, right? So the one value was for the point A will be found at 4 times 10 to the minus 4 and 49 times 10 to the 5. You see? Okay, that's the coordinate of it. So to work on the gradient, it's the change in y all over the change in x. They use the other coordinate as 0 and 0.
Oh.
So when you worked it out,
It
you
gave you
took
that.
49 times 10 to the 5 minus 0 over 4 times 10 to the minus 4 minus 0. So that's how they worked out the gradient of the graph. Remember in maths earlier, when I did the change in y over the change in x, you could have used any other point. You could have even said at strain at your x value is 2 times 10 to the minus 4 and got its corresponding y value and did the difference. You have still got the same value, right? But from what I noticed in module 6, in how they test stress and strain and stuff, very rarely they ask you to draw the graph. What they ask you to do is fill in the table. They'll give you the few values, you just need to fill in the table. What you do in that instance, show how you worked out the stress for one point. So if the first force, so you would have said, you would have worked out the area, right? Pi d squared over 4. You would have got that value of 5,31 times 10 to the minus 4. So you know your stress will be all the forces divided by that, right? So you show the stress for one point, the rest is all the same. Because the mark give you 1 mark for showing that stress formula. They know that you did the rest because of you use that same thing. And they give you 1 mark for all the values. It's not difficult, but it's very rarely tested. This graphs, they hardly test it. Because they'll actually still test on testing these types of questions, that sort of thing, right? But if it does come out, you'll know how to do it. Do you know how to do it?
So the units for the gradient would be no units, isn't it?
Yeah, no, it will be like pascals. Because the units, the gradient gives you Young's modulus. Young's modulus units is pascals. Okay? As you'll understand what I'm saying. Don't worry, you'll be done with the science soon. So when I give you a maths, then you can go home after that. We'll do faster people. Yeah?
Keep practice.
But this is okay, guys. System Young's modulus is okay. 6 formulas. Even when you're doing graphs, you're still using those formulas. Everything we did over here was the formulas, right? Then let's do one more example, example 6.13, and then I'm done. Example 6.13 is like how the roundabout question is. Now take this up. Yes? No?
No, you take that out, honey.
Just
I'll take this.
No more time with my phone in the hand.
Tomorrow you better come ready and prepared.
For?
Wide-eyed with your minds working. Because you know for maths, I'm going to be covering 4 sections. Yeah, so you must know your determinants, you must know complex numbers, trig rules, and graphs, right? And then for science, you must know kinematics, you must know, I want to say dynamatics, kinematics, angular motion, dynamics, statics, hydraulics, right? Oh, and I only tested pumps for the test. I got 3 questions on pumps. No, yeah, minimum is there. Just believe it, guy. It's there, right? But it's not bad. It's everything we did. You'll see. Okay. Example 6.13. Right. So what did they tell you? They tell you that a bolt is 450 millimeters long and has a diameter of 110 millimeters for a length of 200 millimeters. Right? So it has. So its diameter is 110 millimeters and for a length of 200 millimeters, right? And a diameter of 90 millimeters for the remaining length. So what would the remaining length be?
Separate part.
It's really improving,
See, you said it now, now it's popped up now. Okay, so for that remaining length, what would be, what was it the remaining length?
What was the total length again?
450, so this remaining length will be 250, right? I thought you were putting calculators and all that. Right? And the diameter of the smaller one is 90 millimeters. That's the diameter, right? It's round. That's what the bolt looks like. Real life, it won't look like that. No body look like that, right? So, if the bolt is subjected to a maximum tensile force, so it's a pulling force of 950 kilonewtons, right? Calculate the total extension of the bolt given that Young's modulus is equal to
200 GPa.
200 GPa, 200 times 10 to the 9 pascals. This is equal to 950,000 newtons. This is equal to 0.09 meters, equal to 0.250 meters, 0.200 meters. 0.11 meters. Right? All my units are how I would use it in these formulas. They want to know the total extension. This question is like how we did the other question, right? You'll have to work out the total extension of both parts, and then you'll have to add it up, and that will give you the answer. So let's do it. Let's see the big part, right? Big piece, right? That one, right?
Make it a big circle and small circle.
No, right. Let's just go there, right? So, big piece. What do we need to calculate the total extension? We need to know.
Length over there. The length.
Okay, so when this thing is subjected to a tensile force,
How much it expanded? How much it stretched?
it's gonna change by delta x1, and then this end would also extend by
Now takes 2.
delta x2. So the question wants to know what? Delta x overall delta x. Delta x1 plus delta x2. Which formulas do you see that in? Strain, right? Strain is equal to your change in length over original length. We want to work a change in length. We know original length. Do we know strain? No, right? You can calculate. How can you calculate it?
Force over area.
How are you going to calculate your strain? What other formula has strain in it?
Not Young's modulus, or
Yes, I gave you 6 formulas, right?
Wait, we need to
Take away 3 because 3 is for shear forces, right? So I'll give you 3 formulas. After 3 formulas, how many formulas got strain in it?
Young's modulus
And the strain formula, right? And the strain formula. We've established that we can't use the strain formula because we need that to work on the change in length. So which formula would you use to work on strain? Young's modulus, right? Problem with Young's modulus is, do we know stress?
No, we don't have stress.
No, we don't. But can we work it out?
Yes.
Why can we work it out? Because we know the force and we can work on the area. Right? We just did this question like 10 minutes ago.
That was all those funny symbols.
Yeah, that's
You need to get used to it. You need to write it down and, I don't know, say it in your head or something, right? So, for the big piece, we've established the first thing we need to do is get our stress, right? Using our stress, put it in Young's modulus formula to work out the strain. Using that strain value, put it in the strain formula to work out the change in it. That's our process. That's what we're going to do, right? Let's work out the stress.
That's a problem.
So your stress,
Stress.
force
Stress
over,
out already.
it's a round bar. The force is 950,000 all over pi. The diameter is 0.11 squared over 4. So what's your stress? Thought one of you are going to say maths and science or something. So what's your stress?
99965,088.
Give me a.
Engineering.
Yeah.
99.965 times 10 to the 6.
Times 10 to the 6 pascals, right? Which is the same as saying 99.965 megapascals, right? Cool? Right. Now we worked on stress. What was our next part in the process?
I don't work on stress for what? First.
No. Do it. Use the stress to work out strain, right? And that would be done using the Young's modulus.
Whoa, jump it.
Talk to me.
All I need to do is change one.
I'm looking at the right answer there, right? I'm not disputing the answer.
Yes, sir.
That's correct or wrong.
Yes.
But how do you get this 10 exponent 16?
16.
10 exponent 6.
Yeah.
How do I get to that?
Engineering.
See, for me, I would.
On your calculator.
Yeah.
See, there's a button that says E and G.
Yeah. ENG. You just press it.
Press shift in.
Shift E and G.
Not shift, just ENG.
Just ENG. Oh, okay.
Maybe let's press
If you don't ask, you don't really know.
Hey, bro. I have to ask her because I'm gonna have problems.
Right? Right?
Yeah.
Right?
Okay.
So, using this, I'm going to work on my strain, which is equal to stress over Young's modulus. Right? So, this would be 99.965 times 10 to the 6 over. Guys, why am I answering this question myself? We agree?
Yeah.
How are you all okay with calculus, but you're not okay with this?
I think it's the maths. And the test. We think about the test.
Stop thinking about test. Why do you test? Why don't the test will go on to? The test will come.
4.99.
And then 8.
8 to 5.
Just times
And it's fine minus 4.
Minus 4.
That's the strain. Now, using the strain, what can we do? Strain is equal to your change in length 1 over your original length, right? So, your change in length will be equal to strain times length. This would be equal to 4.998 times 10 to the minus 4, and its original length was 0.2. So, how much did it increase by?
9.996.
Anything else?
10 times 10 is minus 5.
Right? So now we worked out the extension for the big piece. Okay? Now let's work out the extension for the small piece. Okay? So same method, right? For the small piece. Okay. So process again. We need to work out stress. Use the stress in Young's modulus formula to work out the strain. Once we get the strain, we can solve for the change in length. Process, right? Okay, so let's work out stress. Stress is equal to force over area. Force is 950,000 over pi. D is 0.09 squared all over 4.
At 0.09.
I think not so bad.
I'm getting 149,330.
563.9. That's right.
Yeah, 149,330,563.
149.331 times 10 to 6.
Pascals, right? Okay. Then using your stress, you will use it to calculate strain. Young's modulus is equal to stress over strain. So therefore, strain will be equal to stress over Young's modulus. This will be 149.331 times 10 to the power 6 all over Young's modulus, which is 200 times 10 to the 9, which is
7.466
7.466.
times 10 exponent minus 4.
Right? That's your strain. Right? Using your strain, what can you do with your strain? Work out the You thought I'm finished the sentence yet? You haven't tell me. Work out the what?
Delta X.
Delta x2, right? So your strain would be equal to delta x2 all over the original length, right? This implies that delta x2 is equal to your strain multiplied by the original length. Your strain is 7.466 times 10 to the minus 4. Its original length was 0.25 meters. You get that value of?
1.867 times 10 to minus 4
meters, right? So the total extension would be equal to your change in x1 plus your change in x2, which is 7.466 times 10 to the minus 4 plus 1.867 times 10 to the minus 4. And that's
9.334. That 10 exponent minus.
I like
Wait, where you got the 1 point?
this was it's not the value. Delta x1 is that value. Actually
Yeah.
that value. 9.996 times 10 to the minus 5. Now, sorry about that. Apologies.
So it's 286.623 times 10 to the minus 6.
286.
Or it could be 2.867 times 10 to the minus 10. I mean minus 4. 2.86 2.867 times 10 to the minus 4.
Multiply by 1,000.
Hey, Papa, where are you getting the 2 from?
It can't be 2, it's 0.
It's 1.8.
Where no, man. Okay, firstly, Trevor's answer is right here. Trevor, I don't know where you getting your number from.
It's 9.996 times 10 exponent minus 5 times 1.867 times 10 exponent minus 4.
Yeah.
Yeah. Even maths and science are the same day, it's not the best thing, yeah? But when I used to teach, Wednesdays were just science.
Which one is first?
Whichever one. Well, I'd say go for the, no. Okay, write the maths first.
1.867.
Write the maths first. You know, I the science is a little bit more. Well, maths took me about an hour to answer that one.
Yeah.
The science took about
That's right.
1 hour, 1.5 hours.
No, right.
So you're about 3 hours.
Okay, right.
Science was
Oh,
always
yeah.
It's at 10 times instead of class.
Mm.
You got this answer, yes?
Yeah, 2.867. Yeah.
Just put it in the calculator.
But all the powers are
Yeah, no, all the powers you get. Because of the way they write the exponent, some you may see like you can still write your value down. No, it still means the same thing.
Now the problem
Whether you write one, see,
times 10 to the power minus 6.
if you write like 2,867 times 10 to the minus 4, right? If I say 0.2867 times 10 to the minus 5,
Minus 3.
right? It's just a matter of moving the comma. If you adding on the exponent, you move the comma one right. If you're subtracting on the exponent, you move the comma one left. Okay?
Yeah. But my calculator is in 3s. I know your picture is in 4s.
Yeah,
There's nothing
mine
in
is
4.
3.
Mine is
But now
in
you're getting
3s.
to the -4.
I moved the
Move the
comma.
comma.
You're moving it.
I moved the comma because he was giving it -4.
Oh.
Yeah.
That's why it's nice to practice the examples on your own too. So you move the comma or you are not moving.
No, I would have just wrote it to
Yeah, that's
So
it.
this is the-
Okay, guys.
to
So that brings me to an end, to the end of
Today.
not today, of module 6.
Oh, hey.
an end of today.
You beat my name, immediately 5 minutes. So, brings us to the end of module 6, which was just strain Young's modulus. Sounds like a very difficult module, wasn't a difficult module, right? 6 formulas you'll know. Stress is force over area. Strain is change in length over original length. Young's modulus is stress over strain. For shear, your shear stress is equal to force over area. Your shear strain is equal to change in length over. That's the same formula. It's just that when you introduce a force sideways, like when you have the 2 blocks moving and you have the pin in the center, or even double shear. Double shear, the only thing you need to remember there is 2 times the area. Right? We've done the stress and strain graphs. This probably the hardest type of question they can ask you, which is still not even that hard. Right? You just got 2 different sizes of the shapes. You work on each part separately, you add the extensions together. Okay, you all just need to practice it.
Yeah, I need to learn the
That is the end of module 6. Does anybody have any questions on this?
Oh yeah.
We're getting there, guys. We're getting there. Right? We got one more module left for engineering science. It feels so good to say that. Right? One more module left for engineering science, which should probably take us a day to do. So probably by the end of this week we'll be done with science. From next week, I can just do past the papers with you. I can even focus on the sections you're having the problems and if we need to do kinematics, some questions there again. What are the ones that are having problems with, like dynamics, statics, right?
maths.
Maths, so I need to do a bit more maths at least. If I can push out the syllabus for maths by next week, Wednesday, yeah, I'll be happy. If I push out the syllabus for maths by next week, Wednesday, Thursday, Friday, Saturday, past the papers, Tuesday, I'll come with it.
You're free.
It's coming together, guys. Soon you'll have your N4 certificate in your hand.
Yes.
Yes.
One flow.
We'll stand, we'll take our pictures.
Slow. Look at my definition.
We are very happy.
This is possible in 4.
And then we come N5 and we do it all over again. Right?
But we told N5 is a breeze.
Who told you that?
You.